Welcome back to the lectures on molecular spectroscopy. In this lecture, let me give you a bit of quantitative assessment of some of the ideas that were presented in the last lecture. If I recall, in the last lecture, I suggested that electromagnetic radiation with different frequencies samples different properties. For example, we looked at molecular rotational motion and molecular structure information being studied by radiation of gigahertz frequencies and known as microwave radiation. It is an optical phenomenon. Electric property of the molecule being studied by the changing electric field in the electromagnetic radiation. And likewise, visible infrared spectroscopy sampling the molecular bond strengths and so on. Okay. We will do a bit of a quantitative assessment in this lecture today with some numbers, and these are what are called the ballpark numbers, or they are also known as the back of the envelope calculations. For those of you who do not understand what is meant by back of the envelope calculations, I must give you an anecdote that long before when you and I were born, internet was not obviously there, and even emails were not there. Only postage and post offices and mail through normal delivery was the order of the day. When scientists declared new results to fellow scientists through postage, very often the new results were checked by the receivers on the back of the empty envelope which was attached to them, and in that they will do small calculations and try to assess that it is indeed a new result that their friend or their communicator has been declaring. So if you recall, we will just do something very similar, order of magnitude calculations or back of the envelope, to three applications, three branches of spectroscopy that you see here, namely microwave spectroscopy, infrared visible spectroscopy, and radio wave spectroscopy. Okay. Let us look at the microwave spectroscopy to begin with. Okay. Radiation frequency range, if you remember, is 10 to the 10 hertz, that is about 10 gigahertz, to about 10 to the 12 hertz, which is 1000 gigahertz, or a terahertz, terahertz. Okay. And this is for microwave. And microwave spectroscopy is used to study molecular rotations, and through molecular rotations the equilibrium structure of the molecule. Now that means molecular rotational energies must be in the range of the frequency that you have here, and the energy corresponding to this frequency, which is given by E is equal to h nu, which if you write is approximately 6.6 to the 10 raised to minus 34 joule second, times say 10 to the 12 hertz, either one of these hertz, which is basically second inverse. Therefore that goes away. So you are looking at the energy ranges between 6.6 into 10 to the minus 24 to 10 to the minus 22 joules. Okay. Now let us see the molecular rotations. Classically, rotational energy for a diatomic molecule, if you have to consider, about an axis, suppose the diatomic molecule is M1, M2, and the center of mass is here, say about an axis which is perpendicular to the bond, because these are the two axes about which the moment of inertia of the molecule is non-zero in the point mass approximation. Okay. So if we do that, the molecular rotational kinetic energy is given by a simple expression. It is given by j square by 2I, where j is the angular momentum of the molecule which causes the rotation, and I is the moment of inertia of the molecule. We will do these calculations more elaborately when we deal with microwave spectroscopy especially, but today's lecture is to give you roughly the magnitude and the scale. So, if you are looking at the, say for example, carbon monoxide, CO, the masses are, let us do simple calculations, carbon 12 and oxygen 16, then the moment of inertia I is given by mu r square, where mu is the reduced mass of the molecule and r is the bond length, the distance between the carbon and oxygen. Let us assume equilibrium and not worry about excited states and so on. Equilibrium, if you do that, then approximate masses for carbon monoxide, if you have to calculate, you do this by 12 grams divided by the Avogadro number, which is the atomic mass, and 16 oxygen mass divided by the Avogadro number. Please remember, reduced mass is m1 m2 by m1 plus m2, where you have seen m1 and m2 are the two masses that you have. So, in this case mu is given by 12 plus 16 by Na. So, you are looking at roughly 12 into 16 divided by 28 Avogadro number. This is the gram. Of course, we would use joules and therefore the SI units we have to use. So, mu is approximately 12 times 16 times 10 to the minus 3 divided by 28 into 10 to the minus 10 to the Na is 10 to the 23 into 6 point something. Let us keep it as 6.022 as 6 point. So, let us do simple calculation. You have 2 and 2 into 16, 32 by 28, roughly keep it as 1, you are looking at 10 to the minus 26 kilogram. Okay. Order of magnitude, that is what you are looking at, and that is mu. Or let us assume that the bond length is somewhere between 1 and 1.2 angstroms. So, even if we keep 1 angstroms, okay, that is 10 to the minus 10 meters. Therefore, I, which is mu r square, is approximately 10 to the minus 26 kilogram times 10 to the minus 10 square meter square, kilogram meter square, which is about 10 to the minus 46 kilogram meter square. This is the moment of inertia. Now, angular momentum for molecules J are usually given in the units of h bar, namely h by 2 pi, and h is Planck's constant. So, even if we take the lowest value for the angular momentum, non-zero value, h bar into some value m, and so let us choose m to be 1, meaning that this is the really lowest rotational energy. If you do that, h by 2 pi is again 6.6 by 2 pi times 10 to the minus 34 joules second is approximately 10 to the minus 34 joules second. Okay. 2 pi is 6.128 or whatever. So, it is about 1. So, let us do the energy calculation now. E as j squared by 2I, you can see that it is 10 to the minus 48, sorry 10 to the minus 68. It is joule square second square. So, let me write the actual units, kilogram meter square per second whole square divided by 2I, and if you recall the I is about 10 to the minus 46 kilogram meter square. So, it gives you about 10 to the minus 22 kilogram meter square per second square, which is the joule. Okay. Therefore, the rotational energy is of the order for a molecule 10 to the minus 22 joules. And if you compare this with the frequency of electromagnetic radiation that is in this range, you know that is h nu, and that is 6.6 into 10 to the minus 34 times nu. You see nu immediately falls in the range of 10 to the 12 hertz, 10 to the 11 hertz. So, the result is that a simple diatomic molecular rotation for an elementary molecule such as carbon monoxide, the rotational energy levels, if they are given by this order, namely 10 to the minus 22 joules per molecule, the transitions between the rotational energies is of that order, and that corresponds to an electromagnetic radiation whose frequency falls in the range of the 10 gigahertz to about 1000 gigahertz. That is the reason why we say that microwave spectroscopy probes molecular rotations, and molecular rotations involve the moment of inertia, and the moment of inertia is of course based on mu r squared. So, there is a bond length information. So, if you extend this to a triatomic or a polyatomic molecule and you want to study the geometry more in detail or more elaborately, of course, that is the part of microwave spectroscopy which we will look at more carefully, but the ballpark figure is gigahertz to thousands of gigahertz, up to in that range is when you can study the molecular rotations. Now, the second one is about molecular vibrations and visible spectroscopy, namely in infrared visible spectroscopy. Here we will go back in the reverse direction. Let us assume molecular bond energies, chemical bond energies, not weaker bonds, namely ionic and covalent bond energies, strong bond energies, are usually between 50 kilocalories per mole to about 100 kilocalories per mole. And a mole is of course an Avogadro number of molecules. So, if you are looking at energy, bond energy per molecule, let us assume 100 and 100 by the Avogadro number 6 into 6.022, but 6 into 10 to the 23. So, you are looking at about 16, 1.6 times 10 to the minus 22 joules. This is kilocalories multiplied by 4.18. So, you are looking at approximately 4 into 16, it is about 6 into 10 to the minus 22 joules. Okay. That is for the, oh, there is also an order of magnitude missing, it is 100 kilocalories, therefore, you multiply by 10 to the 3, and so you multiply this by 10 to the 3, 10 to the 3. So, you get about 10 to the minus 19 joules. This is the energy per molecule due to the bond length, that is, if that much energy you have to provide if you want the molecular vibrations or molecular energies to lead to bond breaking or excitation between different vibrational energies, it should be a fraction of this. Okay. Now, what does this correspond to in terms of the spectroscopic energies? So, if this energy 10 to the minus 19 is to be equated to a radiation frequency nu whose energy is h nu, then you see immediately that this is 10 to the minus 34 times 6, and so you see that into nu, and therefore nu falls in the range of 10 to the minus 4 plus 14 to 10 to the 15 hertz. You see 10 to the minus 19 is equal to 6 times 10 to the minus 34 times nu. So, you see that nu comes to this order. Therefore, molecular bonds are perturbed, or excitation between vibrational energy states of a molecule can happen if you are looking at the order of energies of 10 to 100 kilocalories per mole, that corresponds to frequency of radiation of the order of 10 to the 14 to 10 to the 15 hertz, and 10 to the 14 hertz is 100 terahertz and 10 to the 15 is 1000 terahertz. Therefore, that is the range, and this frequency is typically the frequency of radiation of infrared light. Therefore, infrared spectroscopy or vibrational spectroscopy is studied using radiation of this order, because this order of energy is commensurate to the molecular energy level changes due to vibrational motion or due to electronic excitation. If you have to supply the whole molecular energy, it may go towards a slightly higher level of energy, and that is visible spectroscopy, which creates obviously, which leads to what is called bond dissociation and things like that. You are familiar with the organic chemistry details of chemical processes, light induced dissociation and so on. So, visible and infrared spectroscopy fall in this range of 10 to the 14 to 10 to the 18 hertz, leading to molecular bond dissociation. Now, the last one that you want to look at is a very, very low energy, but it is a magnetic phenomenon. So, magnetic moments of nuclei are tabulated for a large number of molecules, and they are given by a factor, a property known as the gyromagnetic ratio. And it is usually written by a symbol gamma. This is gamma, not nu, and the molecular moment, the atomic or nuclear magnetic moment is given by gamma h bar I. Gamma is obviously of the order of 10 to the 6 to 10 to the 7 hertz per magnetic field, unit magnetic field, which this usually it is reported as per Tesla. T is Tesla, and that is 10,000 Gauss. That is a magnetic field. Magnetic phenomena are explored by a static magnetic field, which allows the magnetic moment to have multiple energy levels, and we will see that more in detail when we study magnetic resonance spectroscopy, but we are only looking at the order of magnitude of what kind of energies are involved. So, if you are looking at nuclei with the gyromagnetic ratio of this order 10 to the 6, for example, hertz per Tesla, then the magnetic moments are approximately this multiplied by the 6 into 10 to the 30 minus 34 joules, and the quantum number I is usually 0, 1 half. 0 is not very useful to us. 1 half, 1, 3 halves, 2 and so on. These are properties we will study. So, even if we assume 1 half as the spin quantum number associated with the nucleus, you are looking at energy ranges between energy levels which correspond to a half configuration and a minus half configuration. So, you are looking at energy delta E of the order of gamma h bar h naught, which is the field, because the magnetic moment will interact with the field to have a certain energy, and that energy is either corresponding to the half quantum number orientation of a proton nucleus or a minus half orientation of a proton nucleus. Therefore, you are looking at energies of this order gamma h bar h naught, and so if you have a 1 Tesla field and your previous values of gamma h bar h naught is approximately 10 to the 6, 6, 10 to the minus 34. So, you are about 10 to the minus 27 joules, I believe. This is hertz per Tesla, h is that. So, the energy is of the order of that 10 to the minus 27 joules, and this obviously corresponds to a frequency h nu. The energy is h nu, the frequency nu, and this is 10 to the minus 34. So, you see nu is of the order of 10 to the 7 hertz. Okay. Therefore, magnetic phenomena, magnetic moments and the detection of nuclear magnetic moments and transitions that happen in the nuclear energy levels due to the energy levels of the nucleus in a magnetic field is of the order of a megahertz, 10 to 100 megahertz for a field of about 1 Tesla. Therefore, radio wave frequency, radio waves have that kind of frequency, megahertz frequency. Radio waves are obviously the appropriate tools, and the magnetic the oscillating magnetic field of the radio waves corresponds to frequencies of this order. So, when you talk about chemical applications of spectroscopy to various fields, one must have a priori some information and some knowledge about what is the order of magnitude energies involved. So, I have given this only by giving you 3 simple examples, but as we see more and more individual techniques of spectroscopy, we will see these things in detail and also much more quantitatively, but you have to have an appreciation of which phenomena that you would be normally interested in when you study a certain type of spectroscopy. This was categorized in the previous lecture, but now with a bit of elementary details, I have also demonstrated that microwave spectroscopy studies rotational motion, vibrational spectroscopy studies bond strengths and bond information, and magnetic resonance spectroscopy studies magnetic moments of nuclei, and therefore the chemical phenomena which are relevant to that. With this, we will see in the next lecture 3 general phenomena of a spectrum that we should look into for detail. Practically every spectrum will need those 3, and they are line positions, line widths, and line intensities, and in the next lecture we will see them. Until then, thank you very much.